should go on 138 when we're done. So, vectors, right? Not new to you. Has two attributes or measures, okay, the word attributes will come up a lot, that it represents. And so the two basic words that we're going to write down first, and the blanks may not be there, magnitude and amplitude are those terms that you used in physics for vectors. Yes or no? But not amplitude. Okay, so what's another way to talk about magnitude? Like another way to say magnitude? Or is that the only thing you ever used? Okay, maybe length. Sometimes it's referred to as the length. Okay. Okay, so what do you think then? So you talked about magnitude and what? What was the other word? Direction. Okay, and direction is the other thing that we were going to put here. You can also think about it as distance and direction, depending on what you're doing with it. But so magnitude and direction is fine, but just know that direction also means amplitude if you see it if you see that word. Okay, so magnitude is your length still, direction is your amplitude, but those words get used interchangeably. But if you're used to magnitude and direction, I mean, we can use magnitude and direction most of the time, but just know that things could pop up in word problems or next year or whatever that could use either one. Now, which one of those two things is the norm for the vector? Magnitude, good. The magnitude is the norm, and how do we notate that? Remember? So if I have vector v, okay, well that's the vector, right? That's vector v. So how do I show that I want that it would be the norm of v? Looks like an absolute value, right? It can look like the absolute value, or sometimes it's a double, like that. Really could kind of be either one, and this is the norm. So the norm is the magnitude. You could see it either way in different textbooks and different assignments and different applications. So what are y'all used to seeing, the one or the two? The one. So then we have a geometric vector, which basically means it's like the picture. It's a representation of a vector as a directed line segment. So this is vector PQ. Would this same vector be vector QP? No, it's like naming an array, right? You got to start with the endpoint. So what do we call this point right here of the vector? It's where you start, but we don't call it the starting point. It could be at the origin, but is it always at the origin? No. How about initial point? Oops. Initial, and then this is the terminal point. Now those for sure are the terms that we use in geometry when we learn it. But then the initial point could also be called, what else did y'all call it? Anything else, or did you even talk about it like this? Okay. Well, it's kind of important to have the words for it because it plays into how we solve some of these things. But instead of the initial point, you could also call this the tail. And that, okay, and head is the word you used here? Okay, because head is a way to do it. Your textbook, along with a lot of other textbooks, also use tip. So have you ever heard the phrasing from tip to tail? Like they just talk about things in general that aren't vectors. Well, you're looking at a vector from tip to tail. You actually go from tail to tip from your initial point to your terminal point. But so tip and tail or head and tail, but if head and tail is what you're used to, that's fine. Like it doesn't matter to me. I just don't need to make it a different thing for you. All right. And I could, instead of having like points here, I could call this vector A also, right? And it could like float right there. That may be more geometrically, you probably see it more with the points, but when you're just talking about vectors doing general things, it may be the lowercase letter there. Okay, so equivalent vectors are congruent vectors that have the same two attributes. That should make sense, right? That's what congruent means. Okay. So parallel vectors they're parallel, just like parallel lines, they could have the same or opposite direction. What about their magnitude? Does it have to be the same? No. Could it be? Yes. So we'll say not necessarily same magnitude. Okay. Could be, but the not necessarily means it doesn't have to be. So, or if they are opposite vectors, then it's kind of like a combination of the congruent and parallel together, and they would have the same, what? These are opposite vectors. What do they have that's the same? Magnitude and opposite direction. What's another word for direction? Amplitude. Okay. Just keep reminding me. All right, unit vectors. Are those things y'all talk about in physics or not? Because I don't know. It's been like longer than you want to even think about it since I've had physics, and I didn't go talk to a physics teacher. So I don't remember if I did that in physics or not. Unit vectors, yes or no? Never seen those before? Okay. All right, so all a unit vector is, it's kind of like doing a little Pythagorean theorem here, and a lot of this is going to lend itself back to just looking at Pythagorean theorem, like little dotted lines on your grid and stuff. If you can make all that make sense, you can make all this make sense. But a unit vector, well, the unit goes with the 1, right? Has a magnitude of 1. What's another word for magnitude? Length. Right? So we use I and J, right? And why it's I and J, I don't know. I even asked some people like, I don't know, but it's always I and J. And you get into like Cal 2 and Cal 3, you're going to have I, J, and K like all over the place. K when you get into the 3 dimensions. But what you need to make sure that you know about this is that the I, this is always the horizontal, and the J's are always the vertical. So it's really not that big of a deal to remember because it's alphabetical just like X and Y is, right? It's the same basic thing. So we know how to, when I want to write an ordered pair and I want to show that it is a vector, how does it look different than a coordinate point that I plot? Well, forget the I and J. No, just a vector in general. You're going to notate that this is a vector and its vector, we'll use what? 3, 2, right? So how do I show when I write it down that it's not an ordered pair 3, 2, like a plot, that it's actually a vector? Use the pointy brackets. We're doing that for the ordered pairs. Okay. So if this is on a grid, this is 3, this is 2, right? So vector 3, 2, is this the notation you've used for vectors? With the point? Oh, you never wrote them in ordered pairs in physics. Okay, good to know. See, these are things I need to know. So if I have an ordered pair, this is kind of a reminder, and this kind of comes up on the top of the next page, but I want to talk about it with this. To show that it's a vector and not like I'm going to start at the origin and go plot the point 3, 2, right? It's not a coordinate point that I go plot. My vector uses these little pointy brackets, okay? And it's always bothered me that I say they're the pointy brackets, so I ask some people, ask Mr. Ackerman, what do they call them? I don't know, I call them the pointy brackets too. So I feel good when he says things like that too. So, so this is the component form, which again it gets defined on the top of the next page. But when you're looking at the unit vectors, a combination of linear vectors or the linear combination of the vectors, basically you see how this is 3 because I have 3 I's and 2 J's. It's like how many units you are on a graph or whatever it is. So this is the same as, so vector R is the same as 3I plus 2J. And if we went down 2 instead of up 2, it would be minus 2J. Okay, so it's kind of a different way to look at it. Instead of an ordered pair, it's a linear combination. Well, good. All right, so a scalar of a vector. It's a what? It's not what? No, what did you say? I didn't hear you. I said a scalar, and that's all I said, and then you said it's not something. I didn't know. Okay. It's a multiplier. A scalar is a multiplier, like a scale factor type of thing, right? But it has to be a non-zero multiplier.
the scalar product
basically uses scalar multiplication. So I know that these aren't on a grid, but we're just going to kind of pretend here. We're going to pretend that vector W is 2, 1. So geometrically, it's just twice the length, but in the exact same direction, right? But it can be in a different place. So if I'm going to use the scalar, my scalar is 3, so I'll say my scalar equals 3, which just saying scalar seems odd to me, but that's the correct way to say it. Like, to me, it's a scalar multiplier, but it's a scalar. Then 2W, oh, I said 3. It's because I'm going to change, well, we'll just change this to 3 then. I'd rather be 3. 3W. Then this is going to be 3 times 2, 1, and you literally just distribute, which is going to give you 6, 3. That make sense? It's like doing a dilation. You just multiply it through. Easy enough. All right. Then we have vector addition. Can be represented 2 ways. All right. The drawing is the geometric, or the ordered pairs would be algebraic. And we will look at examples of those when we actually get to the graph paper part of it. Okay, we all good so far? Okay, shouldn't be blowing your mind with too much new stuff. All right, so component vectors are vectors that are added. Right. And then the resultant vector is a vector representing the sum of the components. And again, we'll look at the actual adding on the graph papers. Well, actually, I don't know. It bothers me. There's not that. We'll do this. We'll make this A, and we're going to make this B, right? And so then we'll make this is A plus B. So the orange is the component vector, and then the purple and the green, oh no, dang it, I got that backwards. The components, because there's plural, sorry about that, the component ones are these two here. And then the resultant is the result. That should make sense to you, right? The two components that go with it. All right, so when you actually add them geometrically, we place the initial point of the second component vector at the terminal point of the first component vector. So I'm going to give you two vectors. I'm going to give you A, and this is the kind of thing that I think you did probably in physics, right? Did you actually take them so you could look at force and stuff like that and put them together? All right. So there's two methods. There's the triangle method and the parallelogram method. Did y'all use both methods? Do you even know what I'm talking about? The triangle, yes. Parallelogram, not necessarily. Okay. So we're going to do A plus B. Right. So here's A, and you just recopy it the best you can. Obviously, we'll be a little bit more accurate with this because we're actually doing something with it. If I'm going to do A plus B, A is the first one, so I put the tail of the second one on the head of the first one. And then I draw the resultant from the initial point of the first vector to the terminal point of the second one, just like I did up there. Bam. A plus B. Make sense to you? Now, it says if more than two vectors are added with this method, the figure that results may not be a triangle. So I'm going to give you another one. I'm going to give you Z. So now we're going to do A plus B plus Z. A plus B. So here's A. Here's B. And again, try and get it, kind of the same direction and length we're not super worried about it right now. I'll give you graph paper when it means more. And here's z. So I'm adding the 3 together, then my resultant right there, it doesn't make a triangle, but it's still called the triangle method because of the way that you go about it. Okay, we all okay with that? Any questions? All right, so then let's look at the parallelogram method, which I guess is new, but it's really not that big of a deal. And I'll give you x and y here. So here's x. And here's y. Ah. So we are going to do x plus y. So we place the initial points of the 2 component vectors together instead of putting the tail of one on the head of the other. So here's x. Try and recopy the best I can here. And then y. We place the 2 tails together like so. Okay. You would use this if you were given something about the vectors and the angle between them. Okay. Otherwise, the triangle method is probably your preferred method. So then it goes on to say, make a parallelogram by placing a duplicate of each component vector beginning at the terminal point of the other vector. So here's x. I'm going to take y and put it right there. And I'm going to take x and put it right there. Then we draw the resultant from the initial points of the original vectors to the terminal points of the duplicate vectors. So from here to there. Top half of the parallelogram drawing will look like the triangle method. If instead of doing what I did with these two, if I had just done the triangle method, wouldn't I still end up with the same resultant? So if you're just to do it because it's your favorite way, kind of seems a little weird because it takes you more stuff. But in an application situation, it may be that that's the information you have, and that's why you need to do it, because you need the angles there. Okay? Because if I wanted to find this and I've got to use, if I know the lengths of them, okay, but I need to find this, then I can use the law of cosines, because if they give me the 2 vectors and the angle between them, I can draw my parallelogram, right? And then if I know this angle, since we know stuff about parallelograms, wouldn't I know this angle? So then I can use the law of cosines there, or whatever. It just kind of depends on the application of it, right? It should be one of those things where when you get to it, it's the only way of drawing it that would make any sense anyway. All right, so vector subtraction. To subtract a vector, you just add the opposite. So see how vector v minus vector w is vector v plus the opposite of vector w. And again, we'll look at an example of this on the graph. I think that'll be better. Orthogonal vectors. Do you know that word? No? Okay. Orthogonal vectors are vectors that are perpendicular. Dang it, where? Oh, sure did. Vectors. Let's see. Any questions about any of the terminology right now? We all good? All right, so then let's go to the yellow paper, have a straight edge handy, and trying to decide which, you know what, since vectors are not brand new to you anyway, we're going to go ahead and just start here. All right, so on this one that has like the graph kind of look, we'll start on that one. And so just title this vectors. It really doesn't matter which one's the front and the back. But this goes on the next page, which is what, 139, I think? Yeah. Let's go on 139. And we're going to look at the vectors from 2 different perspectives. We're going to look at them from the geometric perspective and the algebraic So geometric, we've got them drawn on the grid, right? And then we're going to throw in the ordered pairs for the points on the coordinate plane. So this point right here is at -2, -3. This one is at -1, 0. This is at 2, 1. I'm assuming that you can actually find these on your own. That's why I'm just giving them to you. 3, 4. I just didn't write them on there. But I did draw the vectors just to save us some time. 1, 2, 3. 3, -2. Okay. So those are the ordered pairs, the coordinate points that you would actually go and plot, right? So to come up with the algebraic vector, right, to write as an ordered pair, then what we do is, okay, so algebraic means ordered pair, basically. And we use these brackets. I will tell you, though, vectors sometimes don't use that notation. Sometimes they use parentheses. Cody. Sometimes they use parentheses just like those over there. Do you think that could kind of get confusing? It can totally get confusing. All right. So we will use this most of the time, but if it says vector 2, 3 and it has ordered pairs, then it's a vector. Okay. And I know that's super confusing. I don't love that, but it does happen. So you have to be flexible, right? So to find this ordered pair, all you have to do is, well, let's see. You said you'd rather use head than tip. So head, oh, so I can't spell it. Head minus tail. So the ordered pair for the head minus the ordered pair for the tail. So when I look at vector A, and I'm going to have it in component form, it's this ordered pair minus this ordered pair. So 3 minus 2 is 1. 4 minus 1 is what? 3. For B, my component form is going to be 4 minus 3, which is 1. 1 minus a -2, which is, what's 1 minus a -2? Hard question of the day. Oh, come on. 1 minus a -2. 1, 2, 3, 3. C. That's going to give me -1 minus a -2. -1 minus a -2. 1. And then 0 minus a -3. 0 minus a -3. 3. All right. So what do you notice about those vectors that we wrote down over there? They're all the same. They're congruent, right? Because does a vector give you location? No. It gives you distance and direction, right? Or magnitude and direction. It doesn't give you a location. Okay, now, could I have it start at the origin? I absolutely could. And so if I have it start at the origin, my vector is 1, 3. I'm going to go the right one and have 1, 2, 3. So my vector would look like this. So that I'm at 0, 0 and 1, 3. And this right here is a vector in standard position. Okay, standard position. And your ID makes a great straight edge if you just plop it up there. We all good so far? Okay. So same page down here. We're going to draw vector U, which is, I'll use 2, -5. Okay. So does it really matter where I start? We're just going to find a point. I'm going to start right there, right? So from this point, what do I do to get this? I go to the right 2, and then what? Down 5. 1, 2, 3, 4, 5. Okay, so this is where my arrow goes. Oops. Pen is wonky. And then I'm going to cheat and use my straight edge here. Because y'all get the straight edge, I get 1, 2. So there is u, which is at 2, -5. Okay. You plot it, or you draw it, kind of like plotting points. You're just not necessarily starting at the origin. So what we want is this one drawn or written as a combination of unit vectors. So we're going to draw in, basically make this into a right triangle, just like you would for distance formula or Pythagorean theorem or anything else on the coordinate plane. Kind of like when you learned how to count slope. If I'm going to get from 2 to -5, I'm going to go to the right 2, and then I go down 5, right? And then when I'm looking at this from a unit vector perspective, it's whatever my units are, just the units on this graph. So this is this. Right. Which one's the horizontal, I or J? Horizontal I. So this is like I. And every time you do the IJ form, you don't have to always label all the I's and all the J's. I just want that on your notes so it kind of makes sense. Which means that the linear combination of unit vectors here is going to be 2I minus, because we're going down, 5J. And there's no brackets or anything there. So do you think you even need a picture? If I give you in this form, can you figure this form out? If I give you this form, can you figure this form out? Right? It's kind of obvious. It's just new and kind of weird, but it's really not that bad. Okay. We good with all that? All right, so let's on the other side here. And we're going to do these geometrically and algebraically kind of at the same time. So the first thing we're going to do is 2 times vector c. Now, even if we hadn't talked about the algebraic part of it yet, if I want to copy any of these to what I'm doing down here, aren't you pretty much going to count anyway? Like you would start here and go, okay, to redraw this, I'm going to have to start somewhere. I'm going to go to the right 2 and up 2. Yes, does that make sense? So that is your complete form of the vector. That's why it's really not that big of a deal to figure that stuff out. So whether you do it and you have the actual numbers or you don't, you're still using those numbers. So just talk about it all at once. So let's look at C. What is C in component form? What would the vector look like? How would I write this? 2, 2, 2, right? 2, 2. We agree with that? Does that make sense? So if I want 2 times that vector, then I need to, let's start right about here. That way I have plenty of room. I start here. I'm going to go to the right 2 and up 2. And then I'm going to go to the right 2 and up 2 again. So this right here is 2 times C. Easy enough, right? If we look at this from a scalar multiplication aspect, C is 2, 2. So this is 2 times 2, 2. Couldn't I just distribute those? So what I get is 4, 4. And look, if I start here, I go to the right 4 and up 4. Bam, there you go. What would that look like in IJ form? What it 4I plus 4J. We all good with that? Pretty basic there. All right, so for our second one, we are going to do D plus C. So for D, let's go ahead and get the component form of the vector. What would that be? You have to pretend like I actually hit the points. Okay? 4, 1. 4, 1. which I could, again, I could do this without that at this point, but whatever. So I'm going to start, let's see, 1, 2, 3 down from that. I was trying to conserve some space here. So from this point, I'm going to go to the right 4 and up 1. That gives me this one. So that's my D. Arrows are important here. I'm going to add to that C. So from the head, start the tail of C, and I go to the right 2 and up 2. Draw that in. That is C. Then, where do I start my resultant? At the tail of D, good. And then I go to this right here. And this represents D plus C. So guess what? If I do D, which was 4, 1, plus C, which is 2, 2, all I do is actually add X and X and Y, and what I get is 6, 3. And if I start here, I would go to the right 6 and up 3. There's your component form. IJ form would be 6I plus 3J. Everybody okay with all that? Okay, stop me if you got questions. All right, so now we're going to add, oh, in this, I do want you to write, though, that this is the triangle method. Method. This is the triangle method, or an example of it. So now for number 3, we are going to add B plus C plus A. And I think that we haven't looked at, A and B yet. So the component form of A is what? 2, negative 3, good. And for B, 0, negative 3. Okay, everybody okay with that? We understand how to find those pretty easily and how they're different from, they're never very responsive, so I'm just making sure we're all on the same page here. All right, so now come back down here, and I'm going to start with B. So B is 0, negative 3. So here, 0, and then 1, 2, 3. There is B. Then I'm going to add to that C. So from the head of B, I go to the right 2 and up 2 to get C in there. And then from the head of C, I do A. And from here, I go to the right 2 and down 1, 2, 3. And I draw that in right there. And this is A. So then my resultant goes from the tail of my first vector to the head of my last vector right there. And this orange one that makes all this crisscross, this right here is B plus C plus A. Any questions about that at this point? So let's look at that from an algebraic perspective. B, which is 0, negative 3, plus C, which is 2, 2, plus plus A, which is 2, negative 3. This is probably easier than you want to think that it is. You add all the x's together, which gives you what? 4. You add all the y's together and you get -4. Right? There's your component form. IJ form would look like what? 4i, good, minus 4j. Everybody okay with that one? All right. Number 4 then. This is going to be a plus b minus d. So remember, when you subtract, it's the same as adding the opposite. So it's really a plus b plus the opposite of d. Right? So since d is 4, 1, the opposite of d is equal to what? -4. Let's go back here up here. I don't know if we have room to draw it. But if this is 4, 1, we're going this way. So -4, -1 would be the opposite vector there. You just change the signs on what you have. Okay, so let's start with A. A, I'll start right about here. I'm going to go to the right 2 and down 3. There's A. Then B is 0, -3. Then I'm not using D, I'm using the opposite of D, which I've already figured out what that is. So instead of going 4, 1, I am going to go -4, -1. I'm going to draw that in. And this is opposite of D. My resultant then looks like this. So this is A plus B minus D. All right, so while I pass out some stuff, I want you to get the algebraic and component forms of that one. What did we get for the algebraic form here? Did you get -2, -7? Yes. And did you get -2i minus 2j? Yes? Minus 2j? Minus 7j. I can't read my own handwriting. Yes. Good job. Seeing if you actually did it. Minus 7j. All right. We good? Now, grab this orange one. I want to see if I can do this before the bell rings. You see these top 4, like these vectors they give you to copy? It's kind of algebraic. I didn't want you to guess. That's why I gave you graph paper. And you can't even come up with the ordered pairs yourself because they're not even on a grid, so I'm going to give them to you. So, and if we run out of time, I will, I'll make sure these are in Schoology, but you might be able to write them down. So for the first one, so for vector V, oh, of course, and now my board wants to be stupid. For V, yeah, all right, I'm sorry. I'll text them to you, or I will put them, and I'll put them in Schoology. But just don't try, and you're not going to do the front part on here. You're going to do it on the graph paper that I gave you. It'll be super easy. The back you are going to do on here, and you're just drawing them, not solving them, okay? Have a great weekend. I will see you on Monday.